Hello, this is the first lecture of Math 21. The title of this presentation is Limit of a Function and Limit Theorems. For this lecture, we have two objectives. First, we want to introduce the notion of limits by using an intuitive approach. And second, we want to evaluate certain limits. Now, let us start with the first objective by asking the following question. Given a function f and a real number a, we want to know the value of the function f at points near a but not equal to a. So to illustrate this problem, we will be considering three functions. The first one being the function f given by 3x minus 1. So what can we say about the values of x? For values of x near 1 but not equal to 1. Let us consider these two tables of values here. So for the first table, we have two columns. The first column gives some values of x close to 1 but less than 1. And on the right side of these x values are the corresponding f values. So, for example, when x is equal to 0, we plug in 0 to x, and so we get 3 times 0 minus 1 or negative 1. So this is the value of the function at 0. Now, when x is equal to 0.5, we plug in 0.5 here, so we will get 3 times 0.5 minus 1. We get 0.5 as the functional value. And so on. So, in particular, when x is 0.9999, the functional value is 1.99997. Likewise, let us consider x values near 1 but greater than 1. So, some x values listed here are 2, 1.5, 1.1, 1.001, 1.0001. And the functional values are 5, 3.5, 2.3, 2.003, 2.0003. What do you notice? When x tends to 1, or when x approaches the value 1, from the left side and from the right side, or for x values near 1 but less than 1, or near 1 but greater than 1, the value of the function f gets closer and closer to the number 2. So again, based on the table, as x gets closer and closer to 1, the functional value f of x gets closer and closer to 2. Now let us look at this phenomenon by looking at the graph of the function f. F is linear, so it is represented by a line, this line here. So when x is equal to 0, we have negative 1. When x is equal to 0.5, we have also 0.5 as our y value. And so here, continuing plotting these values here, we see that as x tends to 1 from the left side, the functional values tends to 2. So the functional value gets closer and closer to 2, as you can see in the graph. Likewise, when we consider x values close to 1 but greater than 1, so we are looking at the numbers 2, 1.5, 1.1, 1.001, and 1.00001. The functional values, on the other hand, are getting closer and closer to 2. Now let us consider a second function. So g of x is defined as the rational expression 3x squared minus 4x plus 1 divided by x minus 1. Of course, x cannot be equal to 1. Otherwise, the denominator will be 0. Now, the numerator is factorable. You can factor it as 3x minus 1 times x minus 1. So take note that when x is not equal to 1, g of x is 3x minus 1. So the graph of g of x is very similar to the graph of f, only that the function is not defined at 1. So in the linear graph, we have a hole at x equals 1 representing the fact that 1 is not part of the domain. But as you can see here, graphically, when we take points x very close to 1, the functional value of g is also very close to 2. So in fact, we can use the table of values that we have used for f and plot the same points. We will have the same points. Okay? Because f and g, they're similar. The graphs of those two functions are similar, except that for the graph of g, we have a hole in the line at x equals 1. So for this function g, we also get the conclusion that as x gets closer and closer to 1, g of x gets closer and closer to 2. Now finally, we will consider the function h, whose graph is also very similar to f and also similar to g. But what is the difference? Let us look at first the definition of h. So h of x is given by 3x minus 1 when x is not 1, and 0 when x is precisely 1. So how does the graph of g look like? How does the graph of h look like? So the graph of h is linear. There is a hole in the line at x equals 1, and we have the point corresponding to 1, 0, which corresponds to this part of the definition of h. Now, we can also construct a table of values for h by using the same x values that we used for f. And so, graphing those points, we see that as x gets closer and closer to 1, h of x also gets closer and closer to 2. So now we are ready to present the intuitive notion of a limit by using the previous 3 illustrations as our intuitive guide. So let us take a to be a real number and L another real number. We use the letter L to stand for limit. Now, let f of x be a function defined on some open interval containing a, except possibly at a. We say that the limit of the function f as x approaches a, or as x tends to a, is L, the limit, if the values of f of x gets closer and closer to L, as x assumes values getting closer and closer to a but not reaching a. So we write the limit of f of x as x tends to a, or as x approaches a, is equal to L. So this is our limit notation. So intuitively, using the table of values and the graphs for f, g, and h, we can say that the limit of f as x tends to 1 is equal to 2. The limit of g as x tends to 1 is also 2. And the limit of g as x tends to 1 is also equal to 2. Okay? So, let us review. So, f of x is 3x minus 1. So, we have this line. We note that as x tends to 1, or as x gets closer and closer to 1, the value of the function gets closer and closer to 2. So in this case, we say that the limit of 3x minus 1, or the function f, as x approaches 1 is equal to 2. Note that in this case, the limit of the function as x tends to 1 coincides with f evaluated at 1. So meaning to say the limit of the function is also the functional value at 1. Right. Now, I want you to remember this fact because we will contrast this with the second example. Okay. So g of x, remember, is the rational expression 3x squared minus 4x plus 1 divided by x minus 1. And from the graph, we know that as x tends closer and closer to 1, the value of the function g gets closer and closer to 2. And so we know that the limit of g as x tends to 1 is equal to 2. However, here, note that the value of the function g at 1 is not defined. However, despite this fact, we know that the limit of g as x tends to 1 exists. So this is a major difference from the first example. Now, how about the third function, h? So h is the piecewise defined function where the definition of h is 3x minus 1 for x values not equal to 1 and 0 when x is equal to 1. Right? So the graph of h is this line here with a hole and this isolated point located at 1, 0. As before, we can conclude that the limit of h of x as x tends to 1 is equal to 2 by looking at the graph or by considering x values getting closer and closer to 1 and their corresponding functional values. In this case, the functional values are getting closer and closer to 2. Note that h of 1 is 0 and the limit is 2. So h of 1 does not agree with the limit of the function h as x tends to 1. Now this is a major difference from the previously discussed two examples. So let us mention some remarks. In finding the limit of the function f as x tends to a, we only need to consider values of x very close to a but not exactly at a. Thus, when we are evaluating the limit of f of x as x tends to a, the answer that we may get is not necessarily the same as f evaluated at a. And we've seen this in one of our 3 examples. Also, when we compute the limit of f of x as x tends to a, x needs to approach a from both sides of a, from the left side of a and the right side of a. Now, as a further remark, let us consider this slide. if f of x does not approach any particular real number as x approaches a, then we say that the limit of the function f as x tends to a does not exist, which we sometimes abbreviate as DNE. Alright? So let us consider an example. Consider this function, capital H, defined as this piecewise function here, where the value is 1 when x is positive or 0, and the value is 0 if x is negative. We call this function the Heaviside function. The graph of h is this graph here, right? Now, when we consider points close to 0 but on the right side of 0, the functional values of h are all 1. On the other hand, for x values on the left side of 0 but close to 0, all functional values of h are 0. Now remember that when we compute for the limit of a function at x, as x approaches a, we need to consider both sides of a, the right side and the left side. So can we say that the limit of h as x tends to 0 equal to 0? No. Can we say that the limit of h as x tends to 0 equal to 1? Also no. So in this case, the limit of h of x as x tends to 0 does not exist. We also say that the limit of h as x tends to 0 is non-existent.